As a child, I was always fascinated by how things worked, often taking apart my favorite toys to see what was inside. This curiosity, though sometimes resulting in broken toys, eventually led me to discover the world of Legos, where building and understanding became a joyful process. Fast forward to today, and my curiosity has evolved into a passion for exploring the inner workings of large language models, or LLMs. Many see these models as mysterious black boxes, but just like with Legos, there's a thrill in breaking them down and understanding each piece. In this video, we'll embark on a journey to demystify LLMs, examining them layer by layer, brick by brick. Growing up, my interests shifted from physical toys to digital marvels. Now, as an AI engineer, I find myself working with LLMs, complex systems that many treat as impenetrable. But just as I once explored the mechanics of toys, I now approach LLMs with the same curiosity. With the rapid advancements from organizations like DeepSeek and OpenAI, understanding these models is more important than ever. In this series, we'll peel back the layers of LLMs, starting with basic terms and gradually moving into the heart of their architecture. Let's get ready to open the black box and see what makes these models tick. To understand LLMs, we first need to talk about tokens. In natural language processing, breaking down large chunks of text into smaller, manageable pieces called tokens makes it easier for models to process information. Tokens can be as small as a single character or as large as a word. For example, the phrase, "hold my math," can be split into tokens in several ways: word, level, subword, level, or character level. This process, known as tokenization, is fundamental to how LLMs interpret and generate language. By dividing text into tokens, we set the stage for the model to analyze and predict language more effectively. Many people view LLMs as mysterious black boxes that simply generate text in response to input. However, as engineers and enthusiasts, it's crucial to look beyond the surface and understand what happens inside. LLMs operate through a series of intermediate steps, each contributing to the final output. By examining these stages, we can gain valuable insights into how the model processes information and makes predictions. This deeper understanding not only demystifies the technology, but also empowers us to use it more effectively and responsibly. At the core of every LLM is the ability to predict the next token in a sequence. These models use transformer architectures, which are designed to analyze input tokens and estimate the probability of what comes next. Imagine feeding a model a sequence of 5 tokens. It processes these and predicts the next one, repeating this process to generate longer responses. This iterative approach allows LLMs to produce coherent and contextually relevant text, one token at a time. Understanding this mechanism is key to appreciating how LLMs generate such impressive outputs. Neural networks, including LLMs, don't process text directly. Instead, they convert tokens into numerical representations. Each token is mapped to a unique ID based on the model's vocabulary. For example, the letter H might be assigned an ID of 8, while M could be 13. This numerical encoding allows the model to work with mathematical operations, laying the groundwork for deeper processing. By translating language into numbers, LLMs bridge the gap between human communication and machine computation. Representing tokens as single numbers isn't enough to capture their rich meanings. Instead, each token is represented by an embedding vector, an array of numbers that encode semantic information. These vectors are retrieved from a large embedding matrix, with each vector typically containing hundreds or thousands of values. This approach allows the model to understand subtle relationships between words and concepts, providing a much richer foundation for language understanding. The transformer architecture, introduced in 2017, is the backbone of modern LLMs. It consists of layers that include self-attention mechanisms and feed-forward networks. While newer models have introduced improvements, the core idea remains the same. Transformers process sequences of tokens, capturing complex relationships and dependencies. This architecture enables LLMs to handle vast amounts of data and generate coherent, context-aware responses. Understanding the transformer block is essential for grasping how LLMs function at their core. Transformers need to know the order of tokens in a sequence, which is where positional encoding comes in. Instead of relying on simple indices, Positional encoding provides a richer way to represent the position of each token. This information is combined with word embeddings, allowing the model to understand the sequence's structure. Residual connections help preserve this positional information throughout the network, ensuring that the model maintains a sense of order even in long sequences. Self-attention is a powerful mechanism that allows the model to determine relationships between different tokens in a sequence. For example, in the sentence "the cat slept on the mat and it purred," the word "it" refers to cat. Self-attention helps the model learn these associations by assigning higher values to related tokens. Multi-head attention extends this idea by allowing the model to learn various types of relationships simultaneously, combining their outputs for a more comprehensive understanding. After self-attention, the outputs are passed through feed-forward layers, simple neural networks that further process the information. Layer normalization is applied after each block, stabilizing the training process and ensuring consistent activations. This helps the model learn more effectively, reducing issues that can arise from shifting data distributions during training. Together, these components enable the transformer to build deep, meaningful representations of language. The final layer of an LLM produces a vector with a dimension equal to the vocabulary size. A softmax activation is applied, converting these raw values into probabilities for each possible token. This means the model can predict the likelihood of every token being the next in the sequence, ensuring that the sum of probabilities is always 1. This step is crucial for generating coherent and contextually appropriate responses. Before probabilities are calculated, the model produces raw output values known as Logits. These unnormalized numbers provide insight into the model's internal decision-making process. By examining Logits at different layers, we can better understand how the model refines its predictions as information flows through the network. This transparency is valuable for both debugging and interpreting model behavior. To truly analyze LLMs, we can extract and visualize Logits at different layers using custom tools. By defining classes and hooks in code, we can monitor activations and outputs as the model processes input. This approach allows us to see how predictions evolve, layer by layer, and how the model's understanding deepens with each step. Visualizing these changes provides a unique window into the model's inner workings, making the black box more transparent. By printing or charting the progression of token predictions at each layer, we can observe how the model's understanding shifts and sharpens. Early layers might predict common or simple words, while deeper layers integrate more context, refining the output. This visualization not only aids in debugging but also enhances our intuition about how LLMs process language, making their decisions more interpretable. Through this deep dive, several key observations emerge. First, contextually relevant tokens become more prominent in later layers. Second, the model's outputs tend to saturate at higher levels, with predictions becoming more stable. Third, the final layer's output often appears among the top predictions in earlier layers, gradually refined as information flows through the network. Finally, early layers rely on statistical patterns, while deeper layers leverage context thanks to attention mechanisms. These insights reveal the intricate computations that drive LLMs. Rather than seeing LLMs as inscrutable black boxes, we've explored their inner workings, from tokenization to Logits and beyond. By breaking down each component, we gain a clearer understanding of how these models process and generate language. This knowledge empowers us to use LLMs more effectively, troubleshoot issues, and even innovate new applications. The journey doesn't end here. There's always more to learn and discover in the world of AI. Stay curious, keep exploring, and continue building your expertise, brick by brick.